Hello there. In this video we're going to discuss how to deal with finite power towers and finite tetrations. In particular, you'll learn in this video how to deal with expressions such as 5 to the power of 2 to the power of 7 to the power of 8 to the power of 1, or whatever have you. That is, how to evaluate expressions such as these. And we'll also look at a few properties and a couple functions that are related to tetrations and power towers as well. Alright, so let's just start off with a basic example on how to deal with these types of things. So suppose we have 3 to the power of 5 to the power of 0. What do you think this expression is equal to? Take a moment, pause this video, and think about what you think it is. So for power towers of this form, usually we evaluate, or not usually but always, evaluate from top to bottom. So when you see something like this is the same thing as writing 3 to the power, 5 to the power of 0, or 5 to the 0 takes precedence over the rest, right? So this is the same as 3 to the power of 1, which is of course equal to 3, right? Now note that this is different from the expression 3, 5, 0, where 3 to the 5 takes precedence first, right? Because this is equal to 1, and clearly these are not equal to each other. So it does matter how you evaluate these things, whether you start from bottom to top or top to bottom. But for power towers, we always evaluate from top to bottom. So let's just work through an example in a very basic way to sort of establish why the top to bottom thing is actually the natural way to go about it. So we have 4, 3, 2, right? So this expression is just a bunch of 4s, right? Because 4 is the base of this expression. So it's like 4 times 4 times 4 times 4 times, a bunch of times, right? So we can rewrite this as 4 to the power of 3 times 3, right? Which of course is the same as 4 to the power of 3 to the power of 3. So 4 cubed, we already know, is just 4 times 4 times 4, and this is cubed, and this is of course 4 cubed, 4 cubed, 4 cubed, which is of course the same as 4 to the power of 9, right? And you could have got that from any one of these expressions, but this is the same thing as saying, okay, 4 to the power of 3 squared, where this is 4 to the power of 9, right? That's the same exact thing, right? Which is different than 4 cubed to the power squared. So 4 cubed is 64, and 64 squared is definitely larger than 4 to the 9th. Well, maybe it is, maybe it's not. No, it's not. 4 to the 9th is definitely larger than 64. Nonetheless, they're not equal, right? Alright, so one question that some people may ask is, what is so special about these things? So I'm going to take a moment and focus on tetrations for a moment. So tetrations are a special case of the power tower where each of the levels of the exponentiation process are the same. And we denote tetrations as n tetrated by x. So x is tetrated n times. So this is the same as saying x to the power of x to the power of x all the way up to x, where in this expression there are n levels. So what do I mean by levels? So if I have 4 tetrated 3, this is the same as 4 to the power of 4 to the power of 4. So notice there's 1, 2, 3 levels. Right? So another example, suppose we have the second tetration of the second tetration of 3. So that means we are tetrating the tetration 2 of 3 2 times, right? So this is 2, 3, 2, 3. Right? So what is 2 tetration 3? So that's the same as 3 cubed, and that's the same as 3 cubed. So what is this? So we have a power to a power, right? So we can bring these together. So this is the same as 3 to the power of 3 times 3 to the power of 3, right? Which is of course the same as 3 to the power of 3 to the power of 4, right? So what is this? So we can rewrite this in another way. Instead, we can rewrite this as 3 to the power of 3 to the power of 3, all cubed, right? We can treat this as the power, so pretty much reverse these two things. So this expression is actually the third tetration of 3 cubed, right? So these two expressions are the same. So a question that you may ask is, do tetrations follow properties like exponents do? So question. So is the 8th tetration of the bth tetration of x equal to the a times b tetration of x? Is this true? So we can do an example just to test it, to sort of get an idea before you try proving something that's not true. So the third tetration of the second tetration of x, is this equal to the 6th tetration of x? That's a question we want to ask. So let's choose x to be equal to 2, so we can get some numbers out. Right? So this is the same as 2, 2, 2, 2, and 2, 2, right? And 2, 2 is the same as saying 2 squared. Right, so that's why I chose these numbers, a little bit more easier to work with. So this is the same as 4 to the power of 4 to the power of 4, and we can easily work out this. So top to bottom, 4 to the power of 4 is going to be 256, which is the same as 2 to the power of 512. Right, which is a big number, but I'm going to keep it in base 2 for now. Alright, so let's look at the 6th tetration of 2. So this is going to be equal to 2, 2, 2, 2, 2, 2. So 6 levels of 2. Right? So let's start with the top and work our way down. So this is the same as 1, 2, 3, 4 to the power of 4. And 2 to the power of 4 we can find, that's going to be 16. So we have 2, 2, 2, 16. And then we have what? So 2 to the power of 16 is going to be 2 to the power of 65, 536. And we're comparing this to 3, 2, 2, which came out to 2 to the 512, right? So are these expressions equal? Well, you can compare, since we're looking at the same exact base, which is bigger, 512 or 2 to the power of 25, 536, right? So clearly, this is bigger than that, so these are not equal. Therefore, that power does not work for tetrations. So let's see if we can build a couple properties for tetrations that actually do work. So let's look at the nth tetration of x, which as we know is x, 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 n times. Right? So we can focus primarily on this expression right here, right? So this is the same as x times x, 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 where we have m minus 1 levels here. So this expression can be rewritten as x m minus 1 tetration of x. So this is the first property that we can have. Quick example. The 7th tetration of 8 is the same as the 6th tetration of 8 raised by the power of 8, or the base of 8. Another property, suppose we have xm and nx, right? So we know from the property that we just derived, this is the same thing as x to the power m minus 1 tetration of x, and all of this is raised to the nth tetration of x. So power to a power, so this is the same as x to the m minus 1 tetration of x, multiplied by the nth tetration of x. And we can of course reverse these two. So x, nx, m minus 1x. So we can use our power to a power rule again. So this is x n tetration of x, all raised to the power n minus 1 tetration of x. So what is this? So using our backwards recursion property, this is the n plus 1th tetration of x. So we have mx nx is equal to n plus 1 x m minus 1 x. So easy example. If we have the 7th tetration of x to the power of the 8th tetration of x, this is the same as the 9th tetration of x to the power of 6th tetration of x. So I just want to introduce some properties of tetrational functions in case you encounter them in the near future. So suppose we have f of x is equal to the second tetration of x, which is of course equivalent to x to the x. So one can generate the graph of this to be something like this, right? So it has this little dip. So this dip, one can find with some calculus to be e to the minus 1 over e, which occurs at the point 1 over e, and this point is 1, right? So knowing this graph is probably a parent graph that you definitely should know. And one of the properties that you should know is as x gets close to 0 from the right, the second iteration of x approaches 1. But it's not equal to 1, right? Because we cannot say that 0 to the power of 0 is equal to 1 in all cases, right? This is a conditional form. Now, if we consider another function, g of x is equal to the third tetration of x, you'll get a different type of graph. Namely something like this. Again, it passes to the point 1, 1. So for this, we can see that as x gets close to 0 from the right, the third tetration of x gets close to 0. A very important property that you may already be able to find is that the nth tetration of 1 is equal to 1. And this is true for all values n in the set of positive reals. So take a couple minutes and see if you can prove that if you want. But another easy theorem that you may see from these graphs is the following. So as x gets close to 0 from the right, the nth tetration of x will converge to 0 and 1, depending on the parity of n. So it's going to converge to 0 if n is odd, and it's going to get close to 0 if n is even. So just some properties that you may want to look at. So if you want to look at the function, say 5x is equal to the fourth tetration of x, this graph is going to be similar to the second tetration of x. Namely, it's going to get close to 1, and then it's going to have some dip, or something like that. Right? So this is just a basic introduction to tetrations and power towers. Hope you enjoyed.